Good morning, everyone. Thanks for coming to our workshop. Today we will present the progress of the SOLVERIS project that deals with the in-situ vitrification for radioactive soil remediation. This project is a collaborative research project and is supported by the French government as a part of the French 2030 investment plan. The presentation will be given by Magali Saluden, Head of Technical R&D Department at CEA, Dominique Nozet, the CEO of E.C.I MECA, Stéphane Belbez, expert researcher on contaminated soils on site at BRGM, Mihaela Racapé, Technical Director for Radioactive Waste at Assystem, and myself, Cyril Véronneau. I'm the Research and Development Manager of Veolia Nuclear Solutions, France. Our presentation will cover 7 subjects. First, we will present the GeoMelt In-Situ Vitrification process. That is the process that is the base of the SOLVERIS project. Second, we will describe the structure and objective of the SOLVERIS project. Then we will describe how we select a site for making pilot tests on a real contaminated site. Then we will, Assystem will describe the optimal scenario study for the management of contaminated soils. We will show the result of a small laboratory and small-scale pilot test we made to prepare the real in-situ test. Assystem will show the design on the construction of the pilot unit. And then we will outline the next steps of the project. So let me introduce the GeoMelt in-situ vitrification process. The GeoMelt process was invented in the 1980s by PNNL, Pacific Northwest Nuclear Laboratory. But since then, it has undergone a lot of development and improvement. Now this process is owned by Veolia. There are several versions of this process, but in every version, the principle is the same. If we assume we have a contaminated soil, or a soil in which some waste was buried in the past, we have to insert graphite electrode into the soil and to heat the soil by Joule effect using electricity. As the non-melted soil is an electrical insulator, to start we use starting path made of graphite powder between the electrodes. And as the melting progresses, the melted zone goes downward and outwards the electrode. You can see here the beginning to the end. And at the end of melting, we let the mixture cool, and upon cooling, a durable and stable glass-like monolith is produced. Radionuclides are integrated into a stable and durable vitreous matrix. During the melting, some off-gas are produced. These off-gas are sent to an off-gas treatment unit that can have some scrubbers, some filters, oxidizers. In fact, we adapt the off-gas treatment equipment to the nature of a contaminant. We can make some glass monolith from a few kilograms to 100 tons, depending on the electrical power we're able to supply to the electrodes. But if you want to cover a larger zone, you can make adjacent melt as shown here on the scheme. So the GeoMelt in-situ vitrification process has been used many times successfully, especially in the USA and in Australia. But it requires some development, some improvement in terms of environmental performance, adaptation to French and European regulatory conditions. So that's why the SOLVERIS project was launched with a 5 partner, Assystem, BRGM, CEA, E.C.I MECA, and Veolia. The project budget is 5.8 million euros. The project started in 2022, and its duration is 3 years and a half. In this project, we will demonstrate by tests on a real contaminated site the feasibility of the in-situ vitrification process, respecting safety requirements of French nuclear site. And we will also demonstrate that the vitrified blocks can be safely stored or stocked on site immediately after production. And we should also demonstrate that we can preserve for the very low level waste the ANDRA storage capacity by creating a new opportunity to store on site the very low level waste. Stéphane?
So for choosing a site for implementing this machine, we started by doing a geochemical maps of France for all the metalloids, the silt content, clay content, to have a very precise site-specific geological and hydrological knowledge and site characteristics. After that, we cross this map with the criteria that suit best the ISV system. So you need some silicate, the groundwater must be deep. There is a site characteristic for accessibility, to have facility for treating, manipulating contaminated soil and glass, analyzing, and so on. And we did a multi-criteria analysis using a fuzzy classification system. So each criteria suitable to the ESV was ranked on an Eckart suitability scale, and the relative importance of criteria, utility, soil vitrification, suitability, silicate, aluminate, site pollution, groundwater level, were sampled on 52 nuclear sites, and the site screening ranked the site for suitability, feasibility, so possibility, ready for the test, and too much ready for the test. We didn't want a site which is too easy to test the capacity of the ESV. We wanted some site which was suitable, but also which has some difficulty, so that we can test the efficiency of our system. And it gives.
So thank you. So after the mapping area screening and the result, and according to the result of multi-criteria analysis, so it was important to validate our approach in under representative conditions. The Champ de la Grande Bastide, located in the CEA Cadarage Center, has been selected for a pilot, has a pilot site. So this site is located near the decommissioning facilities. It also includes an uncontaminated area, so this makes it suitable to carry on safe and controlled test. It's also well characterized area, which is representative of the Cadarage site environment, with soil rich in limestone and poor in silicate content. And once the methodology will be validated in the uncontaminated area, we can also carry on a real test in the contaminated soil, which nearby this uncontaminated zone, which presents the same characteristics, the same chemical and physical characteristics. So this is a step-by-step approach to progress from controlled trial environment to apply real condition.
On the framework of the project, Assystem provide a series of engineering studies related to the radioactive waste management. Actually, you talked about vitrified waste or vitrified soil after operation. Primarily, you provide a description of 3 scenarios, and the multi-criteria analysis was applied for radioactive predisposal and disposal solution. The best predisposal and disposal solution were identified. After that, Assystem work on the definition of on-site applicable specification and acceptability criteria for different configuration for radioactive waste storage, disposal, and also radioactive waste transportation. Radiological impact study for on-site and disposal solution of vitrified radioactive waste was analyzed. The transfer vector was water, and different scenarios were analyzed during the studies. A generic safety assessment was given also, and specific preliminary safety assessment were provided for disposal and predisposal site for vitrified radioactive waste. In complement, acceptability documentation of vitrified radioactive waste on CRS and CSA disposal ANDRA site were prepared. And finally, you try to identify the best recovering and transporting solution for the vitrified package through a SWOT scenario assessment, and specific requirement definition was given for the best solution.
Thanks. So once the site was selected and studied, we conducted with BRGM very precise and complete soil analysis. The underground configuration was studied, and we made some laboratory small-scale in crucible vitrification tests. You can see here the crucible with Cadarache soil on the vitreous material we obtained. We also made 200 kilogram scale test in the pilot we have in Limay at Veolia in France. We have a 200 kilogram scale pilot unit for the GeoMelt in container vitrification process. You can see here the picture of the pilot on the scheme of a pilot. You can see here the crucible with 200 kilograms of Cadarache soil. On the first picture, you can see the soil melting. On the vitreous material we obtained here, you can see there's a volume reduction thanks to vitrification. The last picture is a microscope picture, and you can see the vitreous material we obtained is, in fact, composed with two components, a glass, that is the dark one, and a crystal called pseudovolastonite.
So, donc E.C.I MECA is in this project SOLVERIS responsible of the design and manufacturing of the machine and the commissioning test before site of Cadarache. The objective of the machine is to produce a block glass approximately 1 cubic meter. Under the dome of the machine, The soil is heat high temperature, and to have a dimension, the dome measurement is around 2 square meter. We use the 4 motorized electrode that gradually penetrate on the soil, and this penetration is depending of the mechanical resistance, which change with the temperature. The machine, or all the machine, is composed of 4 components: the machine herself, but also a system, a diesel generator with this transformer, the control room here to manage the process data and the data of the machine, and a system of device system for extracting the gas produced during the fusion. We need to have this extracting and filtering and measuring the gas produced under the dome. So here it's to illustrate the situation. You see the control room and the device extracting system is in a 2 ISO 20-foot shipping container. Here you see the control room and the device extracting with a pipe connect to to extracting the gas under the dome. Here you see the platform test in our site with the soil of Cadarache. And here you have a platform test. The dimension is around 16 square meter. And the last picture is for the beautiful overview of the machine during the night and during the penetration of the electrode on the soil.
Thanks. So the next steps of the project is the realization of a test on site. It has started in October. It has just started. The next test is in October. We will test several configurations. We will use radioactive spikes to study the glass homogeneity and durability. We are making some off-gas analysis also, including the particles. On BRGM, we conduct impedance measurement. If you want to say, to explain, Stéphane.
Yes, we were interested in the speed of the fusion of soil, and we researched a way of imaging the whole glass coverage. And so we designed an electrical system to make such measurement and to make voltage impedance measurement, and then make an inversion algorithm, have a 3D, a three-dimensional image of the melted glass. So it's quite an innovative system of modelization, because the temperature is high and the pressure is low. We always know how to modelize high temperature, high pressure, but when the pressure is low, there is a room for improvement and scientific research.
You can see an animation of the whole process, the heating of the soils with the electrodes that go downwards, the melting, the volume reduction, and then the solidification and the formation of a glass monolith. In the project, the objective of the project is also to industrialize the process. So to do that, we need to establish a business plan, and also
we will perform a life cycle analysis. That means testing several scenarios, alternative scenarios to the melting of soil, and see all characteristics, all impact generated by the scenario to help choose the right way of treating the contaminated soil, and the place where we can use our GeoMelt with great success.
So we are very confident for the GeoMelt ISV process on SOLVERIS to be successful in demonstrating the feasibility of in-situ vitrification in France and Europe. Thank you very much for your attention. And our team is available to answer every question you may have in the room just here. Thank you very much.